Let us start again. So what we have to do now is to conclude our proof. So our plan was to prove that all the conditions in the theorem are equivalent, and we would like to do it like this. So we did most of the implications. The only one that is missing is from 6 to 1. And this is actually the most complicated one of the implications, and that's the reason that I wanted to skip it to after the break. So let's formulate carefully what we want to do. So we will assume that the condition 6 holds. So we assume that this is okay, and I have observed that I forgot an F. So we assume that 6 holds. And what we need to show is that 1 is satisfied. That means we need to show that our system of vectors is an orthonormal basis. So to be an orthonormal basis means that it is a basis and an orthonormal system. But the assumption that we have in the theorem is already that the system is an orthonormal system. So that means the only thing we need to show here is that EK is actually a basis. So what we have to do now is to refer to the definition of a basis. That means the statement over here says we need to look at an arbitrary element V in the space, and then we need to show that it can be written in a unique way in terms of what we now call the elements EK. So we must start with an element V in the space. You know, sometimes in the proofs we need to get a good idea, and this is exactly what will happen here. And a good idea is to introduce something which is an element that we just call W. And the way we introduce this is the sum from k equal to 1 to infinity of the inner product between this given V and then EK times EK. When you look at this, you can see actually you would need to show that this is well defined. But this is a quite long proof. So if some of you would like to know the details of that, ask me when I come to the problem session. Otherwise, I'll just say to you that this is actually well defined in the sense that you can prove that this series is convergent. And there's a statement in the book saying that this is convergent. But this is actually a lemma that is not inside the syllabus of this course. So you are not required to look at this lemma to find out why the series is convergent. So therefore, I just tell you it is possible to prove that this is convergent. Then somehow we would like to use our assumption. And the assumption is that if you look at a vector V which is perpendicular to all the elements EK, then you can conclude that the vector is equal to 0. So what we like to do is to consider some integer j. And then we would like to calculate the inner product between V minus W and EJ. And as soon as I've done this calculation, you'll understand why I would like to do it. So let's do it. So here we have a linear combination, V minus W, and we have to take inner product with EJ. So the rules for the inner product says that we can split this out as two inner products. So this is the same as the inner product between V and EJ minus the inner product between W and EJ. And now we can do exactly the same as we did in one of the former proofs, namely to say W has a representation like this. Let's put it in place of W. So this is the same as the inner product V, EJ minus the inner product, and then we get sum from k equal to 1 to infinity, V, EK, EK, and then inner product with EJ. And therefore, now you can see why I actually choose to take inner product with EJ instead of EK. That's because when we put in the representation for the W, then this is in terms of some vectors that are called ek. So therefore I need to call it something else here. So again, we can do exactly like we did before. We can take, we have an inner product with an infinite sum, then we can use the result from your exercise to take the sum out and to take the coefficients out. So this is the same as inner product v ej. We don't do anything with the first term. So here we take the sum out and we take the coefficients inner product v ek out. So what is left is then the inner product starting here with ek and then ej. Actually, it is a little bit surprising, but the assumption that is stated here, that these vectors form an orthonormal system, we do not really use it for anything yet, but we will use it now. So the vectors ek form an orthonormal system. This means that this inner product ek ej, this gives the value 1 if k is equal to j, and otherwise it gives 0. That means our j is fixed. We are looking at a fixed value of j, and then among all the k's where we make the sum, we only get contributions when the k is equal to the given j. And in case j is equal to k, then this contribution is the inner product ek, which is just equal to 1 by definition. So that means what we get out here, we still keep the first term v, e, j, and then here we only get one contribution, namely we get the inner product between v and then the ek, where k is equal to this j that we start with. So that means this is again ej. So what you can see here is we get inner product v ej minus inner product v ej, which is equal to 0. So that means what we have shown here is that if you look at the inner product between v minus w and an arbitrary element ej, this is equal to 0. That means we can use our assumption. It says that if you look at any element in the space that is perpendicular to all of the elements ek, then this is necessarily equal to 0. So what we conclude here is that element we are putting in, this is now v minus w, this is equal to 0. And what this tells us is that this given element v must be equal to our w. And the w is this. So that means we can put this in now. This is the sum from k equal to 1 to infinity, inner product between v, ek, and ek. So that means what we have shown now is that if you consider an arbitrary element v in the space, then this element v actually can be written as the infinite sum of some coefficients times ek. That means what we have shown now is almost what we have in the definition. We have shown that all elements in the space, any element v, can actually be written as a linear combination of, now the element's name is ek, and we even know how to choose the coefficients. So if you look at the definition of a basis, there is exactly one thing that we have not shown yet. Namely, what it says is to be a basis means that all elements can be written like this, but we need to show that the coefficients are unique. We did not do that yet. We have just shown that there exist some coefficients. Now we need to show that there are no other coefficients that will do it for us. So what we need to show is that if we consider the element v, and we know that this can be written as the sum from k equals 1 to infinity of some numbers ck, vk, then we need to show that there's only one choice of ck that will work for us. Actually, what we see here is We already have one choice that works. So what we need to show now is that if v can be written this way, then the coefficient ck needs to be equal to the one that we have given here. So we need to show that ck are necessarily equal to the inner product v ek. And the proof of this is exactly the same as what you will do today, going from this step to this step. Because here you assume that something is a basis. That means, again, you say you know that it can be written like this, and then you need to show that then the coefficients are necessarily given by this expression. So that means what is missing here is exactly what you will do at the problem session at 3 o'clock. So the proof of this is exercise 1. This is actually the very first exercise in the book. So as soon as you have completed this exercise, then we have actually completed the full proof of this statement. So this is a quite long proof. Do you have any questions to that statement and its proof? No? Then let's spend the next half hour just connecting what we have done now with the Fourier series. So, you know, we started the lecture just looking at the Hilbert space L2 on R, but there's a small variation of that space that we need now. And if you go back and you look at your Mathematics 2 book, you'll actually see this notation already used there. So the notation is L2 minus pi to pi. And this space is defined exactly like we defined L2 of R, except that now we look at functions defined on the interval minus pi to pi. So L2 from minus pi to pi is the set of functions f going from the interval minus pi to pi into the complex numbers, having the property that if we integrate from minus pi to pi, the function f of x in absolute value to the power 2 dx, then we get something finite. And exactly like we could show that L2 of R is a Hilbert space, you can also show that this space is a Hilbert space. Exactly the same proof. And let's just write down the inner product. So the inner product is exactly what you would expect. This is again given as an integral, but now because we are dealing with functions on the interval minus pi to pi, this is an integral from minus pi to pi, f of x, g of x, complex conjugated dx. So that means when we are looking at functions in the space L2 minus pi to pi, they are actually just defined on the interval minus pi to pi. But you can easily extend these functions to be functions on the real line. You can say you would like your functions to be periodic. So you say, now we know them on an interval of length 2 pi, and then we just repeat the same functions. So we consider functions in this space, we consider them as periodic functions. So taking any function in this space, we can extend it to a function so we extend it to a function f going from the real numbers into the complex numbers by, and the way we do it is we make a periodic extension, so we just say that f of x plus some 2 pi, this should be the same as f of x. So what this says is that if you start with a function, and let's say we have minus pi here, we have pi here, and we have 3 pi here. So let's say we start with a function defined on the interval minus pi, so this could be something that just goes like this. Then the way we extend it is we go to the next interval of length 2 pi, and then we just repeat everything again. And we do the same here. Something like this. You know what I mean. So what did we do in mathematics 2 for such functions? We looked at the Fourier series. And let's look at the complex form of the Fourier series. So that means we started with the function f, and to that function we associate the Fourier series, which was just the sum from minus infinity to infinity of some coefficients ck times e to the I k x. And the way we defined the ck was as the factor of 1 divided by 2 pi times the integral from minus pi to pi, f of x e to the minus I k x dx. And we had two important statements about Fourier series that I just want to repeat for you. But I would like that we keep this statement. So let's take it here. So the first one is that you remember we had a lot of trouble concerning pointwise convergence of the Fourier series. So we always had to check, will the Fourier series converge for all x? What about points where the function is not continuous? If there's a jump, what will happen with the Fourier series? Will it converge to the average value, or what will happen? We had a lot of discussions about issues of this type. So what we remember first of all that the Fourier series might not converge to the function itself. So the Fourier series, the sum from k equal to minus infinity to infinity, ck e to the I k x, it might not converge to f of x. So it might not converge to this pointwise value f of x for all x. So the classical case where this breaks down is if you have a function that has a jump like this, then we know that the Fourier series will always take the average value here. And that means depending on how this function is defined exactly at this point, we cannot be sure that the Fourier series converges to the right value. So we have a problem here. We had another statement that we used at the end of the course. We had the so-called Parseval identity. Which gave us a relationship between the number ck, the Fourier coefficients, and then the integral of the function to the power 2. So what Parseval's theorem said is that if you look at the number 1 divided by 2 pi times the integral from minus pi to pi of f of x in absolute value to the power 2 dx, then this is the same as the sum from k equal to minus infinity to infinity, ck absolute value to the power 2. And I'm sure at the time where you had mathematics 2, you did not think much about this relationship. You did not interpret it in any sense. But now, with what we know from mathematics 4, I'm sure that you look at this in a completely different way than what you just 5 months ago. Because if you look at what is here, if you forget about the factor 1 divided by 2 pi, you can see what is stated here. This is the norm of f to the power 2. This is exactly the norm coming from the inner product we have here. So the norm to the power 2 is inner product between f and f, which is then integral from minus pi to power f of x to the power 2. So what we have on this side, this is just, if we forget the factor 1 divided by 2 pi, this is just the norm to the power 2 of f. What we have here is an L2 condition. You know, the sequence space L2, this is just the L2 norm to the power 2 of the sequence ck. So what the Parseval identity is doing for us is that it relates the norm of the function to the L2 norm of the Fourier coefficients. I'll say more about that in just a few minutes, but let's discuss the first part a little bit more before we do that. I would like just to formulate one result for you. And this is actually stated as theorem 6.42 in the book. And it says something about the complex exponentials. It says that if you look at the collection of all functions, exactly the one that appear in the Fourier series, namely e to the I, k, x, and you put a certain factor in front of them, namely the factor 1 divided by the square root of 2 pi. So you look at all these exponential functions with k going from minus infinity up to infinity. These functions will form an orthonormal basis for exactly this space. For exactly the space L2 from minus pi to pi. So this means that now we are in a setting where we can apply this theorem. We have an orthonormal basis in a specified Hilbert space. That means we can apply all the conditions that are stated here. We know that all of them are true because number 1 is true. I would like to discuss with you what does number 2 means. This series expansion that says that each element in the Hilbert space can be written as this infinite sum of the elements in the orthonormal basis. Let's see what this says in this special case. So what we need to do is we specify a given element in the space. This is here a v. Now we're dealing with functions, so let's look at a f. So what does our theorem tell us? So we look at theorem 4.7.2, and we look at the second part. So this says that this given element f is equal to the sum. And now you see here, the theory is presented for orthonormal basis indexed from k equal to 1 to infinity. Now we have a different index set. So we are here dealing with the sum k from minus infinity to infinity. So this means now we get the sum from k equal to minus infinity to infinity. And then we get the inner product between the given element f, and then what it says is we have to take the kth element in the orthonormal basis, and then we multiply with the kth element. So that means we have inner product between f, and then 1 divided by square root 2 pi e to the I k x. This is the inner product, and then we multiply with the kth element, so we multiply with this again. So let's calculate this. This is the sum from k equal to minus infinity to infinity. We have this factor, 1 divided by square root 2 pi. We have it again here. So let's take it out here and let's combine them. Then we get the factor 1 divided by 2 pi. Then what is left is the inner product between f and e to the I kx. But this is just f of x, and then we take the complex conjugate of e to the I kx, which is e to the minus I kx. So this is the integral from minus pi to pi, f of x e to the minus I k x dx. And all of this has to be multiplied with e to the I kx. So I think in order not to be confused, let's put a bracket around this, because this is just a number that we calculate and then multiply with this. So let's call this number ck. So then this is the same as the sum from k equal to minus infinity to infinity, ck e to the I kx, where the ck's are exactly what we have in the bracket. So this is 1 divided by 2 pi, the integral from minus pi to pi, f of x e to the minus I k x dx. So then the question is, have we seen this before? And the answer is yes, because this is, now I need to find out where we have stated it. This is exactly what we have here. To the given f, we associate the Fourier series, which is ck e to the I kx, and the way ck is defined is exactly what we have here. So that means what we have here, this is the Fourier series. So that means that this very abstract theorem about orthonormal bases in Hilbert spaces, what comes out when we apply it to this family of complex exponential functions, this is exactly the Fourier series that we are dealing with in mathematics 2. So that means Fourier series, they are just a special case of what we are doing here. But now there's something that is not clear, because up here, if you look at the first point, we had a lot of problems, because the Fourier series might not converge to f of x for all x. This is what we know from mathematics 2, and we have calculated a lot of examples, so this is something we know for sure. There's nothing we can discuss about this. This is something that is clear. But here, we claim, nevertheless, that this always happens. That means we claim that f is always equal to the Fourier series. So why is this not a contradiction? Mathematics 2 tells us that there might be problem with pointwise convergence. Here we claim that the function f is equal to its Fourier series. So why is this not a contradiction? So let's formulate it as a question. So by our theorem, we know that f is equal to the sum from k equal to minus infinity to infinity, ck e to the I k x. And the question is, why does this not contradict mathematics 2? So contradict the statement 2. Or it was not number 2, it was number 1. Bjørn?
Consequence of the equivalence relation we established a few times ago regarding when the function was the same, because we didn't want a function which was not zero in just a single point. We wanted that to be the same as the zero function. So since they just differ in a single point, they integrate to the same. Or the difference will integrate to zero.
So you say something about the pointwise values, or that integrals do not know what is happening in a single point. This is true. I would like to point on exactly what are the differences between the two types of convergence we are dealing with. Here, we get this. This is what we derived from here. Using our theorem, we got that f is equal to this statement. So now I ask you, is it something that has to do with the function values of f calculated at the point x, or how is the interpretation of this? What does this mean? Kasper? Yes. So you say, what this means is that we have convergence in L2, because it is derived from here, and the exact meaning of this is that we have convergence in our Hilbert space. That means we have to look at the difference between the V and the partial sum, and we have to look at the norm in our Hilbert space. So this statement, if we give it a small star, the way to interpret star it is that if you look at the f minus the sum from k equal to minus capital N to capital N, c k e to the I k x, then the norm of this measured in our Hilbert space, which is now L2 minus pi to pi, this goes to 0 as n tend to infinity. So what this means, writing down what this norm is, then this means that the integral of f of x minus the sum from k equal to minus n to n ck e to the I k x, and then absolute value to the power 2 dx from minus pi to pi. So what I have written down here is the norm to the power 2, but that the norm itself goes to 0 is the same as to say that the norm to the power 2 goes to 0. So I can write down that it means this one goes to 0 as n tend to infinity. So that means we have derived that this holds, but this needs to be understood in the sense of this theorem. So this needs to be understood in the sense of convergence in our Hilbert space. And when we write this down, this means that what Fourier series does for us is, for a given function, the difference between f of x and the partial sum of the Fourier series in absolute value to the power 2, we know that this will go to 0 for n going to infinity. And this statement is not the same as the one we are looking at mathematics 2, where we were just fixing one x value and asking for pointwise convergence of the Fourier series for each single point x. So what we get out is this will always hold for our Fourier series, but this is not the same. This is not the same as, and let me just formulate it a little sloppy, this is not the same as pointwise convergence of the Fourier series for all x. So that means it can actually happen that this goes to 0, but that there are some special choices of x where this does not converge to f of x. And this is exactly what we have seen in mathematics 2, that if there's a jump on the function, then in this jump, then the Fourier series will converge to the average value in exactly that point. So on the parts of the function where it is nice and continuous, the Fourier series converges to the function, but there might be some points where it goes wrong. Still, this will always happen, but what we know from mathematics 2, there is a problem with pointwise convergence. So actually, in that sense, mathematics 2 should not exist at all, because we are not looking at the exact correct question in mathematics 2. The exact correct question for Fourier series is to ask for convergence in norm. This is exactly what we're doing here. But in mathematics 2, we cannot speak about norm vector spaces. So we have to do it in a little bit more intuitive sense, and therefore we speak about convergence for special x values, and that's what gives us all these troubles in mathematics 2. But in a certain sense, it is an artificial problem because this is something we need to consider because we are looking at pointwise convergence instead of looking at the real stuff as we are doing here. So what you should know when you go out of the door today is Fourier series, they will always converge to the functions whenever we are dealing with functions in L2 of minus pi to pi. You just have to interpret it in the correct sense, namely in the sense of convergence in norm, which means exactly that this statement is satisfied. Okay, this was the first one. What about Parseval? So let's reformulate the Parseval identity. So that means now we start with the second statement here. And I guess you will do exactly the same as I would like to do, because what is stated here is really the norm of f to the power 2. So let's get rid of this factor 1 divided by 2 pi. Let's move it on the other side. So if you do that, then what Parseval tells us is that if you look at any function f in L2, then the norm of f to the power 2, this is equal to the integral from minus pi to pi of absolute value f of x to the power 2 dx. That's the way we have defined our norm. So now we use the Parseval, we take this factor 2 pi and move it on the other side. Then this is equal to 2 pi times the sum, k going from minus infinity to infinity, of absolute value ck to the power 2. So let's put in these coefficients ck. So this is the sum k going from minus infinity to infinity. And then the way we defined the ck was as the number 1 divided by 2 pi times the integral from minus pi to pi f of x e to the minus I k x dx. That was the number ck, and we had to take absolute value to the power 2. So let's write this in a slightly different way. So let's combine these numbers 2 pi that we have here and the numbers 1 divided by 2 pi that is here. So we get the sum k equal to minus infinity to infinity. So you see, here it is taken to the power 2. So what actually happened is that if you take it out here, then it comes out as 1 divided by 2 pi to the power 2, and then we multiply with 2 pi, so it comes out as 1 divided by 2 pi, and then integral from minus pi to pi, f of x e to the minus I k x to the power 2. So let's take it in again. Let's take this inside the absolute value to the power 2. Then it will move in as a square root. So we get it as the sum k equal to minus infinity to infinity. And then absolute value. And then I would actually like to combine it with the exponential function. So I take it all the way inside here. So we get integral from minus pi to pi f of x. And then we get 1 divided by square root of 2 pi. Because when we put it in here, we get it under the power 2. So we need to take the square root of 2 pi and then e to the minus I k x dx to the power 2. So what is this? This is the sum from k equal to minus infinity to infinity. And then we have an absolute value to the power 2. And if you look at what is inside here, this integral, this is f of x times this function. But this is an inner product. This is the inner product between f and, maybe I need a little bit more space. So this is the inner product between f and then the function 1 divided by square root 2 pi, and then, because in the inner product we always have this complex conjugation, then this is the inner product between f and 1 divided by square root 2 pi, and then e to the ikx, without the minus that we have here. So that means what Parseval tells us is that the norm of an arbitrary vector f to the power 2, this is the same as the sum from minus infinity to infinity, absolute value to the power 2 of inner product between f and then 1 divided by square root 2 pi e to the ikx. How can you relate that statement to the theorem? Yeah, Søren?
Yeah, it's the same as number 4.
You say this is the same as number 4? Yes. In order to say that this is the same as number 4, you need to specify your orthonormal basis. Because what it says is a certain family of vectors is an orthonormal basis, even only if this holds.
Yeah.
So.
But yeah, it's with the orthonormal basis to the ikx divided by square root 2 pi.
Yes, you're completely right. So you see, this is the inner product between f and then the element here. I think I should mark it with another color. So what we had was, here I can write again with a normal, 1 divided by 2 pi e to the ikx, k from minus infinity to infinity. What we saw over here is that this family is an orthonormal basis for L2 minus pi to pi. So this means that the statement we have here, that the norm of f to the power 2 is equal to the sum of absolute value to the power 2 inner product between f and these elements. This is exactly the statement that we have here, which is exactly equivalent to being an orthonormal basis. So this is an orthonormal basis for L2 minus pi to pi. So Parseval's theorem is exactly the same as the statement that was, you said, it was number 4 in our theorem. So that means also the Parseval identity is actually a special case of the theorem that we have here. Now you can see that there are some things that we have not proven here in all details. There are actually 2 things that has not been proved. In mathematics 2, you never saw a proof of Parseval's theorem. And in mathematics 4, you never saw the proof that this is an orthonormal basis. Actually, most of the steps of this proof is in the book, but I did not show all these details for you. So you can see that they are equally hard. If you can prove one of them, you have the other one for free. So if you go to the book and you check the proof that this is an orthonormal basis, then by this statement, this means that you also have proved this statement, meaning that then you have a proof of Parseval's theorem. Or you can look at it the other way around. If you are able to give a proof of Parseval's theorem, then you know that this condition is satisfied, and then you can go back and say, then you have a proof that EK is an orthonormal basis, that means then you have a proof that this family is an orthonormal basis for L2 of minus pi to pi. But I just tell you, I have not done any of these two steps, but we know that they are equivalent to each other. So I hope that this sheds some new light on Fourier series for you. We will come back to that more later in the course again. So, yes?
Is it okay that there it goes k from 1 to infinity and there from minus infinity to infinity?
What we are doing when we are dealing with the sum from minus infinity to infinity is that you always deal with the symmetric partial sums. So you always look at the partial sum going from minus n up to the same n. So what happens is, if you go from a different lower index up to a different upper index, then you get a more complicated results. But as long as these limits are minus n up to n, then it's the same, then it's okay. We can speak more about it at the problem session. So if there are no more questions, then let's stop here for today.